Okay, I'm super happy that we could convince Peter Dueben from the European Center of Medium Range Weather Forecasting to talk about the digital revolution of Earth system modeling. So Peter has been with the center for a while, and he's now recently become the head of Earth system modeling. And Martin is giving a little bit of a better introduction to Peter, but I'm super happy he's here. Thank you, Peter.
Thank you, Torsten. As Torsten mentioned, Peter is the head of the Earth System Modeling section at the European Center for Medium Range Weather Forecasts, or ECMWF, where he develops one of the world's leading global weather forecast model. He arrived there from for being University Research Fellow at the Royal Society, and he focuses right now on the Maelstrom Euro HPC joint undertaking, which is implementing a software hardware co-design cycle to optimize performance and quality of machine learning applications in the area of weather and climate science. Without further ado, the stage is all yours, Peter.
If I manage to unmute myself, yeah, thanks. Well, thanks a lot for inviting me, Torsten and Martin, and thanks a lot for giving me the stage. So I'm going to talk about the digital revolutions of Earth system modeling. As both Torsten and Martin mentioned, I'm basically working at the European Center for Medium Range Weather Forecast, and what we do at the European Center for Medium Range Weather Forecast is medium range weather forecast. So we build basically global model prediction systems. We have our own supercomputers, and we have basically we are a research institute with kind of 150 researchers basically having the common goal, as it says on the slide, to kind of build these kind of very big, large Earth system modeling systems. And if you don't take a lot from this talk, it would be important to kind of get this one single message, basically, that Earth system modeling at the moment is really experiencing kind of quite a disruptive change, which also offers great opportunities. And I'm not normally bringing this slide up, so it's kind of really exciting times, and I'm apologizing for the kind of all those buzzwords like revolution and disruptive and everything, but I think it's really at the moment kind of quite a tricky time to some extent, because things are changing quite fast. But also this means that we are actually able to kind of improve our prediction systems in principle. So I'm going to talk about 3 different revolutions that have happened and are happening at the moment. The first one is what we call the quiet revolution, and that's really something that happened ever since kind of ECMWF was founded and kind of started to develop those global model simulations, that we basically over time really improved our systems quite drastically. And this is a plot that is showing you the forecast accuracy that we had at the European Center. And the x-axis you see time, it's really over decades, and on the y-axis you see the forecast quality going from not so good to basically very good at the top. And the different colors that you see in the plots are different forecast lead times. So the forecast quality of a 3-day weather prediction in blue here is better than the forecast quality of a 5-day weather prediction. It's better than a 7-day weather prediction and a 10-day weather prediction. And what you should really get from this plot is basically that the forecast accuracy is increasing over time and quite drastically. So basically we see something like 1 forecast day per decade improvements. And this is mainly caused because we get better observations about the Earth system. We have better models. We have better data simulation procedures where we can kind of make more use of those observations, but really also because we can increase resolution of our models. And this is basically coming also from the increase of compute power over time. So as we had basically this kind of steady progress, that's something that Peter Bauer and others coined as the quiet revolution over time. And it's something that we can basically be proud of. And it tells us that if you have steady investment into kind of improved weather predictions, you basically get also better, something useful out of this. And we're not at the end there, in a sense that we can still kind of progress over time. But at the same time, things became a little bit more tricky in the year of something like 2015 and so on, where we basically realized that we will have to also engage with what we call the digital revolution. And to show you what this is, I brought you the figure on the left. Here you have the different supercomputers that we worked with at ECMWF, and with the different peak performance over time, increasing from left to right. And then you have the resolution that we could work with in global model simulations of the atmosphere, also going basically kind of from 250 kilometers all the way to something like 10 kilometers that we work with today. And as we now approach the exascale, this plot is from 2018, so you can probably say that we kind of now are somewhere here. we actually approach the level where we can kind of work with 1 kilometer global resolution. And that's quite important for us because on the diagonal here, you see the different features that we can resolve as we increase resolution. And for 1 kilometer, we basically make a step that we can resolve deep convection and also surface drag. So we basically are able to resolve like topography fields, for example, like the Alps in a very much detail, and that really will help us to kind of improve our results significantly. And also deep convection, it's basically like large thunderstorms in the tropics that are really very important for the energy cycle of the global atmosphere. And we will basically be able to get rid of parameterization schemes that typically represent those kind of large thunderstorms, clouds in global simulations, and they bring a lot of uncertainty into the simulations. So we know that as we kind of increase to 1 kilometer, we will basically get very good results. However, the problem comes in if you look into the sustained performance. So you have the peak performance on the bottom and the sustained performance that we worked with at EaseNWF on the top. And what you can see is you started with something like a factor of 2 between peak and sustained, and it went down over time to something like basically a couple of percentage. You can argue that if you now kind of port to GPUs, you probably have a fraction of a percentage of the sustained performance in comparison to peak performance. So it's quite bad, right? We basically are not able anymore to kind of make very good use of the supercomputing facilities we have. And in this context, we basically proclaimed that we should have the digital revolution. And this basically means that we need to kind of change how we're building systems. So until then, we could basically just build like Fortran code, and we could just kind of wait for the next chip to come out and bring us more performance. And now we really have to rethink of how we actually build the models in principle to be able to kind of really leverage the performance that you, for example, get from GPUs and accelerators, because to port like the standard code, the standard state-of-the-art code written by domain scientists to GPUs is really almost an impossible task. So we basically acknowledge that we should kind of head for this digital revolution and to basically rewrite the way of how we build these models. And this includes that we kind of need to think about new methods and algorithms. It includes also that we need to think about machine learning. It includes that we kind of need to think about domain-specific languages, for example, where we separate the concerns between the domain scientists and the computer scientists. And it also means that we should think about really more of like how to use the heterogeneous processing and memory architecture. So how to basically shift data around and so on and so forth. And this basically means that we need flexibility, we need efficiency, we need portability, and it basically means that we also need to kind of rewrite our models and kind of make them basically fit for the exascale. And just to give you one example, what this could mean in terms of the digital revolution, there's a lot of things that we've done. One of the more striking ones is basically that we also looked into new dynamical cores. So the dynamical core is basically what represents the fluid dynamical component of the model. And so far, we were working with kind of a Fortran code, something like 1 million lines. We were working with a so-called spectral model, which is extremely efficient in terms of the time stepping, because you can work with semi-implicit schemes that allow you to do very long time steps. But the problem is that you need to kind of transfer between spectral and grid point space in every time step. And therefore, you need different transformations. And one includes the so-called Lejeune transformation that is kind of scaling with n cubed, where n is the number of grid points along the equator. And that's not very good if you want to increase resolution, because eventually you basically spend almost all the cost of the computation in the Lejeune transformation. So we basically knew that we need a new dynamical core on the long term, but we also knew that we need a new kind of compute environment in the longer term. And therefore, we basically went to develop the new dynamical core, which is called the finite volume model, so FVM. It's basically should be integrated in our integrated forecast system, so the normal atmosphere model as a dynamical core in the future. And the aim is to really have like high resolution capabilities because there's not the Lejeune transformation limiting you. There's high efficiency and high scalability. And we also want to get performance portability. And here in particular, we also kind of engaged a lot with Torsten's and Torsten's team and the Swiss groups by also kind of picking up GT4Pi basically into the dynamical core. So we rewrite FVM in GT4Pi. And this will also kind of allow us now to kind of go to step into the Python world, if you want, which is to some extent important because we can't expect anymore to have like the brilliant PhD students coming out of university with 3 years of experience in Fortran coding. So we also need to adjust to what people are using as a language. And also, in particular for machine learning, it also opens a lot of doors, obviously, because the machine learning world is basically the Python world. So we are able to kind of not only change our die core, but also our compute environment. And GT4Pi, I assume that everyone here knows about this because it's a Swift kind of effort, really. But it basically allows you kind of to separate the front end in the model development from the back end, where you kind of put it onto different architectures. So it's kind of separating the concerns to some extent about where you can run the model and how you can port it. And at the moment, we basically have a global configuration that we want to use for EaseNWF, but we also have this kind of a local configuration that is, for example, used in the group of finally at ETH, but also at our member states. They can basically use like local area model simulations, where you basically have exactly the same die core that you use for a simulation that has a couple of meters resolution, all the way to the global simulation where you have like 10 kilometers, for example. And the target is now that we kind of not only push the dynamical core into this framework, but also kind of to think about the physics, and in particular also kind of to port to the GT4Pi Next. That will also allow us now to kind of work with unstructured grids, because so far we basically hope mainly looking into the portability of the structured grid, but which is not ideal if you want to go to the sphere. The tool is basically holding what it's promising. So on the right, you can basically see weak scaling plots for Pete Stein on the one hand, and also for Lumi on the other. So you have two very different computer architectures, but you see basically that the weak scaling is working fine all the way to thousands of GPUs. So it's holding the promise in a sense that it kind of brings you efficiency and scalability and portability. In terms of the model itself, we have the die core now working well on structured grids and very efficiently on multi-GPU simulations. We're now porting to the unstructured grid version, basically, and kind of now we haven't basically tested that one efficiently, kind of with the efficient compute environment, but we're getting there. And by the end of the year, we basically want to have like similar plots that you can see on the right, also on the unstructured grids. And this is really, as I said before, we're very grateful basically for the support as well from the Swiss part. So PASC, EDH, CSES, they are all extremely involved here, and we're kind of basically using their tools, and that enables us as well to kind of build this die core. Regarding the digital revolution, there's also one more thing that should really be mentioned, which is the program called Destination Earth. So it's kind of a big European Union program, and the idea here is that you build digital twins of the Earth. Digital twins is also yet another buzzword, but basically what this means for us is that we're basically building extremely high resolution simulations, and they should be basically so good in quality that even a domain expert couldn't really separate them, like distinguish between the observation and the simulation anymore. So if I would show this plot here, where you have on the left side, you have the simulation, on the right side, you have the observations, even the domain experts couldn't really tell you anymore which one is which. So that kind of fulfills for us kind of the need for a digital twin. And it also means that we're now kind of building a digital laboratory where you can explore, for example, what happens to climate change. If you, for example, change the vegetation in the Amazon regions or these kind of things, you can now kind of put this into this digital laboratory and play around with this. And via this Destination Earth, we basically also received a lot of funding to kind of really realize this digital revolution. So we kind of really can use this resource now to kind of really push the models into the new regime, and that they will be able to easily run on kilometer scale simulations. The Destination Earth, or the short form is Destiny, is basically providing kind of us with the ability to build what we call the digital twin engine. And here the idea is really that you kind of build like packages, in particular EaseNWF as well, that you can use kind of all over the place for the different model centers in the world. And this basically allows us now to kind of think about high-performance computing adaptation, to kind of build workflows that, for example, not only run on EaseNWF machines, but also on Lumi and Leonardo and Mare Nostrum and so on and so forth. Think about I/O and data workflows, make them efficient, software management, controlling workflows in cloud environments, and visualization engines, basically, that should all be developed within Destination Earth and then can be used basically for a lot of different model centers. And what we really, or what Destination Earth to some extent already has achieved, and it's only like 2 years old, is that now global kilometer scale simulations are already kind of doable on a much easier way than it was the case like 5 years ago. So 5 years ago, we basically needed a machine like Summit and a lot of work to kind of start a single simulation. For example, nowadays, kilometer scale simulations can already run more or less routinely on machines like Leonardo and Lumi. It's still a lot of work, there's no question, but it's kind of getting there in a sense that it's really easy to kind of spawn off those simulations. And the hope is that we will get basically more realistic on the local scale. So on the left, you, for example, see a simulation of the Arctic where you have the sea ice cracks that you can see in the simulations, and they are kind of quite important to get like the thermal interactions between the seawater and the atmosphere right. And they can now be resolved in those simulations, for example, which wasn't the case before. You will get more realistic global scale as well, in a sense that you see a lot of kind of different features working together with each other and interacting on the global scale simulations. And also you have a system that is very much nicely coupled, and also you get the coupling right. So what you see on the right here is basically a video of surface winds and surface wind gusts. And what you see is basically that the topography is nicely visible, but the topography is actually not even plotted. It's basically just coming out of the physical fields that you kind of show on the figure, because you basically have the nice coupling between the surface wind and the land surface schemes in those high resolution simulations. So basically, the message from this slide is those simulations really are becoming available and standard. You get what you also want to see in terms of like the local features. So for example, there are so-called medicanes, which are like small tropical cyclones in the Mediterranean Sea, for example. And as you increase resolution from left to right, you can really see how the medicane is kind of really taking shape, and you get the wind speeds that are kind of much closer to what you would expect from observations. So you're getting there in terms of the quality for the local features there in particular. And also, we are now able to perform very long simulations. So on the right here, you see a video that was performed from a climate twin simulation of destination Earth, and that's a 4.5 kilometer simulation. And that's now performed really for, I think, more than 10 years, which is kind of also kind of quite new, that you can run those model simulations fairly easily into kind of decade-long simulations. So it's not only weather anymore that you can look into, but also climate timescales. And then just to convince you again about the benefits that you get, you have benefits on the local scale. So this one shows you, for example, the medium surface temperature over Poland in the next gem simulation, which is another set of longer term simulations. And you can nicely see that the cities are kind of coming out quite clearly. So Warsaw, for example, has basically a much higher temperature than the surrounding area, which is the kind of the urban heat island effect. And with those high resolution simulations, so left is the observation, and in the middle you see the high resolution simulation from Destiny, and you can see that we also now picking up these schemes. This also required some model development. So this is a high resolution simulation of the old generation, where we didn't really have the urban scheme that we're now using, but kind of with model development and high resolution, you really get the details right as well. And there's also the global scale. So there's an oscillation that is called the Madden-Julian oscillation. And I'm not going to be able to explain you exactly what it is in 2 minutes. But I can basically tell you that it's really like an oscillation that is kind of happening on the global scale. And it's typically extremely difficult to get these kind of oscillations right, even though they are very important, for example, for Indian monsoon and other features. Because they are also very much depending on the local scale and kind of convective systems, for example, in the tropics. So what we basically see is that those large kilometer scale simulations are also helping here, and that it's also now really important to run them actually for a long time, like 10 years, for example, to get information about the Madden-Julian oscillation. And you end up kind of to be with a 4 kilometer simulation, you end up to be much closer to the observations than you are with, for example, a 9 kilometer simulation, which is kind of the standard of operational NWP at the moment. Okay, that's one side to it of Destination Earth. The other side is also that we should change our workflow to some extent and make the systems more usable. So another kind of big component of Destination Earth is also that it's kind of should be more interactive. So what we had in the past, or in the current system, is basically that we perform large-scale simulations for weather and climate, and then the impact sector is basically getting our information, and then they share it with the users. But there's not much of a upstream interaction happening here. And with Destination Earth, this workflow should basically be changed in a sense that there will also be upflow, the ability of the impact sector, for example, to spawn new simulations that then will run on the EuroHPC machines. And this will also kind of be able, and there's also kind of an effort from Ormond's side and ESA to bring the users and the user base closer to the data and to the observations to kind of really make it more interactive. Okay, so that was the digital revolution. It's still ongoing, and now let's come to the machine learning solution revolution that is kind of obviously also coming these days. So this is a slide that I presented in 2020, which sounds like ages ago in machine learning standards. And it's basically about probably the very first global weather simulation that was performed in deep learning that Peter Bauer and I kind of published in 2018. So basically is one of the first paper that I looked into machine learning ever. And what we've done there is basically we took like reanalysis data and we tried to kind of build a global weather model using deep learning tools. The deep learning tools were extremely crude by then. But we kind of managed to get something that looked really very much like the reanalysis data. So we basically building a model from scratch from just using a lot of data about the atmosphere. And we get something that looks like the atmosphere. So if you kind of compare the left and the right, for one of the first forecasts, I think that was done with kind of machine learning models, you see that the dynamics is kind of working very well. The forecast error was comparable if you kind of compared like with like. It was clear that there was a lot of happening, a lot of papers were coming out these days. But I still asked the question in 2020, is this a future for medium range weather predictions? And I basically concluded that this is kind of unlikely. And my reasons why this was unlikely was basically that the simulations change dynamics in long integrations. So the model simulations were not stable. It wasn't kind of quite clear how to increase complexity to something that could really kind of build a huge Earth model in principle. And also, it was unclear how to kind of fix feature interactions and how to kind of make sure that we kind of get the right interactive the right interactions between the different components. And we also only argued that we only had 40 years of training data and was very unclear whether this was enough. All of those concerns to some extent have turned out to be kind of invalid to some extent. So we are now able to build like global machine learning models. We are also able to kind of interact with the features well because the architectures have developed so much over time with kind of now basically UNets and all those structural transformers that can really kind of learn a lot of interactions between the different components and so on and so forth. The data has turned out to be enough. And the complexity is kind of now also no point anymore because we can really build some of the biggest HPC applications are now machine learning applications. So basically the concerns from 4 years ago turned out to be invalid. And to some extent, the developments have kind of taken up at an incredible speed. So this is the first paper that we brought out in 2018. In 2020, we basically posed a benchmark challenge, so kind of benchmark data sets for global weather predictions. And then it took 2 years where kind of there was not too much happening in terms of like steep progress. And then Ryan Keisler published a paper where he basically showed that you can do these models and those models are extremely efficient and they're actually also quite good. And then it only took like a couple of more months until Huawei and DeepMind and Google and Microsoft and others have basically published models that were competitive with the quality of our conventional models. Also to notice NVIDIA, where they kind of spend a lot of effort and time to kind of develop ForecastNet, which is now also very nice. And they also proclaim this kind of Earth 2 framework where you basically should be able to kind of build like interactive models as well in the future. So a lot of the developments have really kind of overtaken themselves. And from 2020, where people were still extremely skeptical, even the most progressive ones like myself were very skeptical, even though I think it's fair to say that Thorsten knew all along that machine learning would take over. The field has changed in a sense that we're now in a stage where we know those models are competitive, if not better than conventional models. And on the left, you see a plot that I've stolen from the GraphCast paper. It's a very boring plot to some extent. It shows you the lead time on the x-axis for the forecast and the different quantities that you look into on the y-axis for the different pressure levels. And whenever this plot is blue, it basically means that the GraphCast model is better than our own forecast system at EaseNWF for deterministic predictions, which basically means they can beat us if they want to. And that's true for Google. That's also true for ForecastNet. However, there was still a lot of uncertainty in the community, mainly because those models were different, right? So you knew, for example, that those models were smearing out into the future. So on the left here, you see this is a plot of the Keisler paper, where you see on the left the truth of a global field kind of developing over time. And obviously, in the truth, the structureness and the shape and the sharp gradients kind of remains the same as you kind of impose it over time. Whereas in the deterministic machine learning model, you can really see that it's smearing out over time, which makes sense because you train for root mean square errors. But it basically is something that still the community was very skeptical about. And there were a number of open questions basically that still had to be addressed. Like, can these models avoid the smearing of the long-term predictions? Can they learn uncertainties the same way that they can basically do like root mean square error predictions? Can they extrapolate in a sense that if there's a new extreme event coming that has never been there before in terms of like a drought or precipitation or something like this, can these models actually do this? Can they represent extreme events in that sense? Yeah, that's basically the same point. Can they be trained from observations? Because at the moment, those models are really trained only from data simulation, which is then basically, again, built on conventional models. And then also, can they represent physical consistency? So is a weather prediction actually physically consistent, or is it just producing a small root mean square error? So in 2023, basically, we took our time and looked into all the details. And we've published a paper basically on what we kind of have found in terms of the different forecast qualities and so on. And it really turns out that these models are competitive, not only in terms of scores, but also in terms of the physical reasoning, what they do and stuff like this. So the community has really kind of built a lot of trust over the last year, I would say, into those models, because they basically provide not only a score-driven result, but also basically a nice physical representation of what's happening. And that's not only true for normal weather, but also for extreme event, which is obviously also very important. We have kind of supported this by putting a lot of those models, so including ForecastNet, GraphCast, and Pango Weather online. So we kind of now running them routinely every day. And by doing this, we push basically the charts, so the weather predictions online onto the web page. And this also allows the community to kind of get used to them a little bit more, to kind of really start building trust in those schemes. We've also, in the last year, built our own machine learning model we call the AIFS. So our conventional model is the IFS, and now we have the AIFS as the artificial intelligence forecast system. And we also managed to kind of now go up in the ranks to some extent and have a competitive model now with the leading models that are published. So in some of the results, like for example, surface temperature, surface 2 meter temperature, you basically beating the kind of the state of the art, if you want, with GraphCast and other methods. So that's all developments within 1 year. It's kind of what I would call quite disruptive. And if you now kind of compare the quiet revolution, so that's the plot that I showed you before, with the machine learning revolution, so it's the same quantity we're looking into. It's a different time scale. So this one starts with 2004, so around here. And you see basically the quiet revolution progressing over time. And this is the AIFS, so the machine learning kind of model quality that we have there. So there's really a step change to some extent into a new level of quality that would take a couple of years development basically from the quiet revolution time. What about climate? That's a very good question. So the weather community is now getting really used to the fact that you have to think about machine learning weather forecasts, and also the weather centers in Europe are really kind of picking up those developments and are now also building local models and so on. But the climate community is still extremely skeptical. They have some good reasons to be skeptical to some extent, because if you train a model for nowadays climate, but then the climate is changing, you don't really know what's going to happen there. I'm personally getting more and more optimistic that the machine learning models can do this, but that's still something, a community to be convinced, if you want, from how much you can do with machine learning. You can ask the questions like, why was the whole approach of kind of these global weather prediction systems so successful, and why did kind of companies like Google, Microsoft, Huawei, NVIDIA get so much interested in them? And I think the main thing that kind of really pushed the limits was that that there was a very good data set available that could be used for those model simulations. So there was the ERA5 reanalysis, which is basically a representation of the atmosphere for the last decades. And it can be downloaded freely. It's kind of nice in a nice format where you can easily kind of port it into the Python world and play around with it. And it was also kind of it's there, it's available, it's of high quality, it's a good reference, and everyone could basically just work with it straight away. So that really kind of made a big difference. So open data sets continue to be very important. And that's also something that we kind of pushed in the milestone project that Martin mentioned at the beginning, which actually has now finished last month. But it's basically really something that we try to kind of embrace, that we kind of build high quality data sets there. So what can the machine learning model do and what can they not do? It's something that is kind of my personal opinion, and maybe I show this slide in 4 years from now and say that was a 2024 slide and now everything is just changed in the meanwhile. But basically, I'm pretty convinced that conventional models will not disappear. So machine learning models will beat them in a lot of prediction scores, but it's still very important that you have the conventional models in the backup. Just imagine what it would happen if there would be a volcano exploding in Sicily or something like this. The machine learning models wouldn't even know that these volcanoes exist, right? So they still need physical reasoning for a lot of things. And also, if you're a forecaster, you also want to have like a 3-dimensional representation of the full atmosphere and all the physical beauty. And not only the forecast itself, but also an understanding what's happening. So physical models will still play a role in the future. You can also now say, okay, why still do destiny? Why still do these kilometer scale simulations? We should just kind of push all the efforts into machine learning. And I would also disagree with that one, with the main reason that kilometer scale models will basically bring you also like a huge amount of data sets that you don't have. So the kilometer scale models basically bring you the data that you can use for machine learning and training in principle. And also there's still this kind of climate time scale where we really don't know exactly how much we can trust those models. So again, the digital revolution that is still ongoing is important and will still continue. You can basically say, however, on the other side, it is fair to say that most of the predictions that people are using every day will come from machine learning models in the future, and that has already started. So if you kind of take your own like Android mobile phone thingy and you kind of look into the weather forecast of Google, it's probably going to be something that has already been at least manipulated by machine learning, and maybe still not like a pure forecast, but definitely something that has been post-processed. And machine learning is the perfect glue between models and observations. So we're going to be able to kind of extract much more from the observations as well in comparison to the models because of machine learning, because you can really kind of put one data set into the context of another seamlessly in the future. And that's a big point. If you present this basically in a climate audience, everyone will revolt, but I'm pretty much sure that also machine learning will really make a difference in the climate projections. So the models are getting so trustworthy to some extent, and also we are able to kind of really get more of the essence of the climate systems rather than just the model fields that we kind of treat as an image, that we will also be able to kind of tackle extrapolation problems in climate, I'm pretty sure. Big questions at the moment. What about data simulation? Langwen here in the audience has just published a paper about data simulation. So it's still something that hasn't been touched so far in the same scale as weather prediction. So data simulation basically takes observations and puts them into the model state to kind of generate initial conditions. And the reason why it hasn't been done so far in the same amount is because there's not the same type of training data set quality available. So people need to do a lot of work until they actually can do data simulation tests there. The other thing is we still don't have a full Earth system model. So if you want to do seasonal predictions or climate predictions, you basically also need an ocean model. And it's unclear how to build an ocean model because you don't have the data again, because you don't know what's happening in the deep ocean, for example. You don't have a good reference data to learn from it. So we are now hiring people actually to kind of build an ocean machine learning model as well, and a CS model, and a wave model, and a land model. So this is going to happen, but it's still something that has to happen. And we still will see kind of a lot of developments in this area. And also, we need to also go away from just the training of reanalysis data. We also need to go kind of towards the training of observations. So for example, you could nowadays not just do a model step and a post-processing step, but you could basically just do a model and post-processing step together if you train from synoptic observations, so kind of ground observations that are really trustworthy. But that's another step that we need to take, and then you can probably easily get another 10% improvement of quality of results for those fields that are really mattering for society, who normally tends to live at the surface. Okay, there's also a question like how much you can kind of combine the conventional models with machine learning models, and there's a good paper that came out around a tool called NeuroGCM from Google, where they basically have taken the speedy model, which is a dynamical core, and they plugged it into the training workflow of a machine learning tool. So they basically train a machine learning adjustment to the model fields through the dynamical core, because they have basically written the die core in JAX, and they can auto differentiate through the core itself, and they're getting very interesting results. They can basically learn the model physics, something that really is kind of quite a troublemaker for conventional models, by using machine learning in this die core framework. And they also kind of now achieving simulations that are really kind of running nicely over decades. So they can perform what we call an AMAP type simulation, an atmospheric model intercomparison project simulation. So it's a special protocol. It's still no climate simulation because you don't have an ocean. You just prescribe the fields. But they basically get results that are really kind of competitive with the best AMAP models that we have so far, which are also including kilometer scale models. So there's clearly more to come. So what is our aim today? And as a community, basically, what we obviously should push forward the kilometer scale digital revolution. We should push forward the machine learning revolution, but we also should really think about how to make our tools more usable. And to do this, basically, what we would need is a kind of a better framework that people can just kind of go to an entity and have all the observations data set next to all the modeling data sets, and they can easily kind of plug and play the different data sets together. They have machine learning tools that are kind of basically easy to use because they have been tested in a similar reference. If you, for example, want to do like downscaling exercise over in Switzerland, you should be able to just kind of take an architecture that has been used over Austria or Italy or something like this, and just plug and play your tools into it. The tools should be scalable. They should allow like a lot of like physical testing as well with unsupervised learning. They should allow for visualization that is basically coming out of the box and be scalable. And users and scientists should be as little kind of concerned about the technical problems, basically. And to do this, you really need those bigger projects. You need Destination Earth, but you can also kind of trust in projects like Eve, which is a very large scale project that really wants to kind of push basically the limits of what we can do and bring together the community to build like more global schemes. But that's something that individual model centers can't do anymore. It's something that really needs to kind of be done on a very large scale, and we're getting there. And talking about a very large scale, we probably also should talk about foundation models, and kind of with generative AI as a new buzzword again, yet another one. It's important that we kind of look into this as well. And I brought you another slide from 2020, which is a slide where I tried to kind of summarize what the different application areas are in the field that, of weather and climate modeling. And each of those boxes here is basically a different application area, and they're spread all over our workflow from observations to post-processing. And back then, all of those boxes were single GPU applications, which was fine. By now, all of those boxes are multi-node applications, which is getting trickier. If you wait for a while, then models like AIFS will be a large-scale compute system, and you will really need to think about like what to do in terms of the capacity of what you have in terms of GPU computing power in Europe. So the question is whether you can centralize this to some extent, also having this kind of the last slide in mind where you want to unify efforts. And here, it seems to be quite obvious to me that we should really think about a unification of the machine learning applications by building like a European foundation model. There have been first attempts. There's a paper around AtmoRep from Christian Lessig et al. Christian has started at ESWF and is doing a perfect job to kind of push this there as well. That really wants to kind of go to representation learning approach where you can really kind of build like a tool that understands what weather and climate is doing. And then you can use these tools for a lot of the different application areas. And the last couple of weeks, I've been quite busy writing a proposal, which is called the Weather Generator, where actually Torsten is also one of the partners. And the aim here is really to build a tool that can be used basically as a foundation model for weather and climate. And that should then also be extended and put into the context of the Destination Earth program. And with this tool, we should be able to basically tackle a number of applications, not just one. So you do the training big time once on a supercomputer, and then you can basically apply them for 22 applications that we kind of name in the project proposal, but there should be more. And this is really something that we should develop as a European community. So just to summarize once more, you started with a quiet revolution in the 80s, going all the way to 2020. Then the digital revolution took over from 2015. It's still ongoing, but it's probably kind of in the second half. And now the machine learning revolution took over, and I think I'm pretty confident that now the generated foundation models will actually kind of be the next step change that we will see. And if you look into talks like, for example, Jensen's keynote at the GTC conference or something like this, he's not even talking anymore about conventional modeling, right? So this left half doesn't even exist anymore. And I wouldn't be surprised if also the machine learning part is not something that the cutting edge of HPC will kind of talk much about in the future. I think it's really the foundation model part where the models are really kind of scaled up to very large applications that's going to drive the HPC part. Okay, just one slide on the work mode. I think that's also kind of very much important to realize how the work mode has changed ever since in the last 15 years with climate modeling. So in 2010, a single person could really understand what the whole Earth system model was doing. We were working with 1 million lines of Fortran code. The code was in tarballs and shared there, and we basically were still running CPUs, and Moore's law was still happily fine. Then people realized that you actually need like a big effort to kind of make the models ready for the next steps. And this kind of basically led to the digital revolution. People like Tim Palmer basically mentioned that we need something like an Airbus 380 effort in Europe to kind of build those models. You should not kind of build very small models everywhere, but you should build like one big model that can then serve the whole community. And he was successful in the sense that in 2020, the work mode has changed. The models are so complex now that an individual person cannot understand everything anymore. Moore's law is dying. We're now porting successfully to GPUs. We still kind of store the meta information locally, but also a lot of the data is already available online, and it's kind of pushing towards the clouds. And we're obviously using code repositories, and the workflow has changed there a lot as well. And in another 10 years from now, we're going to work a lot with those 10,000 lines of Python code that you will need for the machine learning models. There's still a question going on whether we will have hundreds of models that are kind of built for specific purposes or kind of a couple of foundation models. And I'm pretty sure it's going to be a couple of foundation models. And what's also going to change is we're going to walk further towards HPC that is federated and data that is federated. We're already doing this with Destination Earth, for example. So in 2020, we were only able to run on our local machine and a couple of other supercomputers with a lot of effort. And now we routinely run on a number of zero HPC machines, for example. So this has already changed in a sense, and it will change more. It will be less important where you run your model in principle. Another thing that obviously is important for our community is how we interact with the tech giants. So as you've seen, all the tech giants have been investing into weather forecasts, which is absolutely new to some extent. I mean, it was something that was a public domain, and we as a weather center, we really need to understand what this means in terms of the future for us. But it's something that, yeah, we need to figure out and kind of to make sure that we don't really that we still gain from the brokers, but that we also kind of still own some of the process, because weather forecasts need to be a public good to some extent. Just to mention it, we held a MOOC, a massive open online course last year. And if you're interested in this kind of field of weather and machine learning in principle, please have a look, because the MOOC is over, but the material is still online. And we were ourselves very surprised by the uptake by the community. So we had more than 9,000 registered participants, which is kind of quite unheard of in our field of science. Normally, I don't even think that the whole community has 9,000 people. So it's was quite successful, and it shows you once again kind of where you will basically be able to hire the good people in the future, I guess. So the last slide, what have we learned? There was a quiet revolution over decades that kind of meant that we had brokers in the field. There is the digital revolution still ongoing that is pushed by kind of big projects like Destination Earth. And it's really helping us now to kind of perform those kilometer scale simulations routinely. There's also the machine learning revolution that has started a couple of years ago and is still in full bloom, and no one knows exactly where it's going to end. And all of this basically means that we have quite a disruptive change in the community, and we actually really see also the benefit of it in terms of better models, better tools, and also kind of going towards a federated HPC data structure that also will help in the future. And I think for me, the big thing is obviously to make ECNWF fit for the machine learning models with AIFS and these tools, but really also kind of to push now for a European foundation model for Earth system sciences, because I think that's really going to make a difference. Okay, that's all I had to say. Thank you.
Thank you, Peter. I would like to take the occasion right now to advertise the next BCast that will be happening on the 18th of April. In 2 weeks' time, we will have Peter Pietzuk from Imperial College London, who will be talking to us about Cherry. Now we will move to Q&A. I can already see that we have 2 questions. Maybe we'll start with Langwen. Should be able to unmute yourself.
Okay. Yeah. Thanks a lot, Peter, for your nice presentation. So firstly, I would like to ask, well, you already present a lot about the conventional weather simulation and also a lot about machine learning simulation and also a lot of things about what will happen in the future. So, well, an obvious question would be, what will it be like in 10 years? Where does the machine learning model sit and where does the traditional model sit? Because now it seems like a parallel effort and don't really rely on each other. So what will things look like in the future, 10 years or maybe 20 years?
Yes, I mean, we're already producing machine learning forecasts right now, right? We're already pushing the data from AIFS online. It's not what we call operational to some extent, but we basically already there that we have operational type model simulations that we're running on a daily basis, and also so it is no question that there's going to be a parallel stream of conventional modeling and machine learning model that are running next to each other. The weather community is fairly conservative. So it took the community something like 25 years to actually kind of really embrace ensemble simulations, for example. They're not going to just suddenly switch to machine learning and everything is going to machine learning. So we will have those 2 models in parallel for the time being. And also that makes sense because we need to prepare as well for like the unseen weather condition. And there we want to have a physical understanding and basically we will continue to run the conventional models, but obviously a lot of efforts will we will not be able to kind of spend the same amount of effort for both streams that we had for one stream at the beginning. So there will be a lot of kind of movement in terms of efforts there as well. The big question is more like what's happening. I mean, for the forecast, it's clear. The bigger question is what's happening to data simulation. There's going to be also machine learning data simulation happening. There's going to be seasonal prediction with machine learning. There's going to be the first climate type simulations with machine learning. And basically, you will have both of them in the same time, but machine learning will take over still a large fraction of the domains where it's not really having a lot of influence yet. So this is also going to happen. Yeah, what else was the question?
Yeah, but now the problem is, according to your presentation, the growing rate for the machine learning regime is much faster, maybe an order of magnitude faster. And maybe at our current state, the 2 looks similar, but what if like 5 years later, 10 years later, you suddenly get a much better?
I mean, as I said before, I think for 99% of the applications of weather predictions, you will probably use a machine learning model in the future because it is going to be better. For a lot of forecast scores, for reliability and stuff like this, we will. I mean, there's not a big question anymore that those scores are improved if you want, and that's also what a lot of people are using. But for the 1% of the predictions, I think you still would want to have a physical model at least as backup to kind of understand what's happening there. And there are also tasks that the machine learning model cannot do yet. For example, there has been this Saharan dust event like last week, right? I don't know whether you have seen the dust as well in Zurich, but this is something the machine learning model can't do. And it's not only that it can't do, but it's also difficult to believe that it can do it from the training data that it has. So there's still reason why to have a physical model, but the fraction, I think the resolution, for example, that we're working with at ECNWF kind of had a steady increase, and we always kind of pushed the limit to what we can do. I think there's less pressure on kind of going towards extremely high resolution anymore. There's more pressure on kind of building as well a good machine learning model in the same place.
Okay, thank you. Also, I would like to ask, what about some a little bit longer term predictions, such as season to season regime? where does it sit? For example, what's the current state and how good does the machine learning model performs in that regime?
Yeah, so there are different timescales. Like there's the nowcasting where machine learning is clearly beneficial. We knew this we knew this in 2020. Then there's a medium range weather prediction, like a couple of days all the way to 2 weeks, where it's now clear, okay, machine learning models can beat the conventional scores. Then there's a seasonal prediction, which is looking a couple of weeks into the future. There, machine learning is basically still on par, not really shown. They're still not the killer paper yet, and it's also a bit trickier because you also need to represent the ocean as well, which these models typically don't do very well yet. But I'm very confident that this is going to change soonish. And then there's a timeline scale where you kind of run like for years into the future. And there you do not only have to fight the quality of the model, but you also have to fight, if you want, the concern of the scientist. So if you make a prediction 80 years into the future, until the end of the century, who will be able to tell you whether the prediction is right or wrong, right? Even if you have a machine learning model and you do perform all the different tests and tick all the boxes about like how you kind of looked into your model, you will still not be able to kind of really say whether the model is doing something useful or not unless you wait for 80 years. And that's going to be a problem for those models. But honestly, I wasn't convinced that those models can do long-term simulations 2 years ago. I'm nowadays very convinced that that's something that I would trust in with the developments that are now happening. And also, again, it's as you move to kind of bigger and bigger models like foundation models that actually kind of extract the essence of the physical system rather than just a forecast score based on an image coming in and image going out, you will also be able to build more trust, and those models will become more physical. So, but it's an open question. If you ask 10 climate scientists today, 9 of them will tell you that machine learning can't do it.
Okay, thank you. Okay, so the last maybe minor question. So you mentioned that the FEM model will be pushed for unstructured grid. So I'm wondering what kind of unstructured grid that you are going to use, and to match the performance of the structured grid, is there any special treatment?
Well, you have different grids that you're working with, and there are grids that are structured like longitude, latitude, but then you have problems with the poles. There's grids that are unstructured, like the grids that we were normally working with in IFS, that basically have a structure in the Y direction, but sorry, a structure in the X direction, but not a structure in XY. And you basically you have to kind of be able to deal with them to kind of get on the sphere like an isotropic distribution of the grid points. And that's the reason why we want to look into this. I mean, they're also kind of structured equivalents like the cubed sphere that you could look into. But basically what we want to have with FEM is a model that can run on all of those grids. And then you basically need to be able to work with unstructuredness.
Correct. Thanks a lot. I leave here to others.
Thank you.
Okay, Lex.
Hello, thank you very much for the presentation. I really enjoyed it. So first, to also follow up on what you discussed with Langwen, one of the things which to me seems I currently can't really follow is if you have ML models that are based on mostly current data or past data.
Yeah.
And in the context of climate change, how do you train these so that they are capable of seeing things that don't exist yet or haven't outside their scope? So you, in my experience, interpolation, things that are in the range of what's been happening,
yeah,
very good at. Outside the range seems a bit wobblier.
No, absolutely. I mean, that's exactly the question. I mean, and not only how to train it, but also how to trust them. And I mean, there are different approaches. You can train those models in climate type simulation. So you can run the model, a model like a conventional model into the future, and then you can use this as training data and then understand it, but then you will not be better than the model itself. You can also argue that if you are, for example, sitting in Switzerland and you kind of you have a global model, then the global model will see what's happening in Italy. So if Switzerland is getting warmer, then you basically will still be fine because the model has seen this climate. But there's a fundamental problem there. On the other hand, it's not what we see. So we train our forecast systems at the moment, like the machine learning models, for example, until something like 2018 or so, and we can still use it happily in 6 years later climate. And we have never seen a problem in a sense that the model was running out of the climate of the data range, for example, right? So these models seem to be more robust than you would actually think. But it's still not a good feeling there, in particular if you want to predict 80 years into the future. So there's still more work to be done. But as I said, I think in particular also this kind of push towards foundation models will help there, because you will not only extrapolate within your data space, but you will actually extrapolate in the latent space and so on. You will probably also be able to kind of make more robust tests with those models, because you have one model for 20 applications. So you will kind of test them in anger if you want, for a lot of different applications, and kind of figure it out. So I don't have an answer to your question, but I'm optimistic that we will kind of be able to do that in 5 years from now.
But so from your talk, and what I understand is that you believe that there is still, even in, let's say, 5 to 10 years, when machine learning models are doing a lot of work, there is still a place for the, let's say, conventional models, for the classical microphysics and radiation models and so on.
I think yes, and it's also that nowadays at DSNWF, it's also a nice process to see that the machine learning developments are kind of also now dragging into the conventional developments to some extent. So the same people are looking actually in the precipitation fields for conventional and ML models, and therefore there's also some convergence there in a sense that I think you need more conventional developers as well for machine learning models in the future, because you're looking more into the details and so on. So this kind of the two worlds will merge more, even if they are still using a different basis of a model, basically. I don't think, yeah. So I'm pretty convinced that in 30 years from now, we will still have a conventional model running at DSNWF. But it's probably not going to take 80% of the compute cost when it's running up here. That is 80% of the size of the computer that is when it's running operational, but rather a small fraction.
I see. Okay, thank you very much. Thank you.
Thank you. And now Timo.
Yes, thank you for the nice talk. I had one question. You presented this plot of efficiency over time, right? Basically, of conventional models. Do you have a similar plot for the efficiency for the machine learning based models that you showed?
You mean the forecast quality, right?
No, the forecast quality you showed how it improves, but in the very beginning of your talk,
you mean the
talked
sustained
about
against
how
peak
much
performance
percent of the peak performance can actually be utilized by these models, and we saw that there was a huge downward trend. So now, but I'm wondering, how is this trend looking for the ML-based models? So are they also an answer to this problem?
I don't know the exact number. Maybe someone else here in the room would know, like, what the sustained versus peak is for training of large language models, for example. But I assume they're going to be more in the 5 to 10% range rather than the 0.5 to 1% range. So I think I mean, just from the architecture, you have an extreme benefit there, right? Because you basically have dense linear algebra rather than some sort of kind of very diverse kernels with very different feature size of like how they use the compute for the different parts of the model. So, and also you have low numerical precision, you have everything you need for like a fairly good sustained performance, right? But actually, I never diagnosed the number, but if any, I'm pretty sure someone in the room has done. So if anyone has an opinion, let me know. No one is shouting out. Okay. Maybe that's something we should look into.
I guess that was your question, Timo. And Benjamin.
Hello. Thanks for the nice talk. I really enjoyed it. I have a DSL specific question. So maybe for context, I worked 3 years at DSLs at Métier Suisse, so including GT4Pi and Dawn and grid tools. And I also very strongly agree that I think there's a really good vision to stop using Fortran to write weather climate models, but use some nice Pythonic language. At the same time, I also see that Explain right now is porting a huge Fortran code base icon to GT4Pi. Now I think you guys want to again port a huge Fortran code base into GT4Pi. And I think it's a bit unfortunate that there seems to be this catch-up game where the model is first written in Fortran and then being ported and rewritten in Python. And some people have the vision that maybe in the future it will be the other way around, that the model is written in Python or in a Pythonic DSL right in from start. And I wanted to ask a bit, what's your view on this? Because right now it does not feel very, very,
yeah.
yeah.
I mean, IFS, the model that we have is basically 40 years old. FVM is 10 years old. So it's not that these models just kind of suddenly disappear and you can write a new one from Python, right? You have to do the step once, I guess. It's fair to say as well that languages are not as important anymore as they used to be. So the thing that I haven't talked about is that we're also kind of using to portability a tool called Loki, which is very similar to Cyclone that they kind of use in the UK, and they basically already transform like Fortran code into other code, basically. I mean, the transitions between the different code bases is also getting more and more easy, right? So I don't think that this is going to be our main concern in 10 years from now, that we're still kind of developing in Fortran and then porting to Python. I think it's going to be more like, once we've done the thing now for FVM, this is it. We're going to develop FVM in Python. The physical parameterization schemes, it's still a longer process. It's not going to happen in the next year or something like this, but there's going to be a Python version then. And I think also in terms of just thinking about who we are hiring in 10 years from now should make us think, right? I mean, we can't really trust anymore that we will get a good inflow of Fortran programmers, and we can't really trust anymore that any people building Fortran compilers. And I don't want to start now a discussion about efficiency in Fortran and stuff like this. It's a minefield, obviously, but I think the software environment will also make a huge difference for conventional model development. And this not only means the language. I think the language is almost secondary. It also means like how we are kind of working with a different code, and that we're developing on a modular basis. For example, the different physical parameterization schemes, that model developers are just looking into kind of Python with a nice capability of plotting while they develop, and so on and so forth. I think it's more than just the language. I think the language is probably the smallest problem.
Yeah, I also strongly agree. And maybe you could add some of your views on this, because I also feel like one issue for a motivated HPC engineer to get into kind of climate and weather is a bit the accessibility with just running these models, getting the data and things like that. Maybe you can add some of your views on this.
I mean, I feel you. I totally understand what you're saying. I think we are on a good track. I mean, we are pushing the models to be open source, kind of as much as we can, basically, and we're making good progress there. The model code itself is revised and engineered in a sense that we now that we kind of separate the concerns with approaches like GT4Pi and so on and so forth. It is still, we're not good yet, right? It's still a huge effort, for example, to get IFS running on a new supercomputer, and that will kill us eventually. We will need to be very flexible, and we will need to be easier and kind of also embrace more, make it easier for people to access the code and to get started. But we are on a quite good track. So we have published, we've open sourced our radiation scheme, the cloud scheme, the convection scheme, the land surface scheme, the wave model scheme, and so on. And we not only open source them, but also package them in kind of nice formats with CMake configurations and everything, that it's fairly easy to download and run them by now. So we are, I hear you. We are on a good track, I would guess, but we're a slow community in principle with these changes, right? So we're talking about a decade timescale rather than a year timescale. So.
Yeah, I agree. And I mean, I think also, for example, Explain has very clear goals with respect to making these things more accessible. And I think it's very clear, right? It's a good investment, because if you, I mean, I don't know, you put out the data set and then ML people give really good results, everyone benefits from that. It's kind of the same here. So my last question would be that very often in the group, I tell my fellow colleagues that climate weather models, the computational patterns that are really important are stencil computations. And then at the same time, I know that IFS has a spectral method model. And I always feel a bit like, is this what I'm saying? How true is it? And also, I would be interested how true do you think this will be in the future, that like classical climate weather models will be stencil computations? Or do you maybe also see that different numerical patterns will come in and will become more relevant?
I wouldn't expect a revolution happening there, in a sense that I don't think that the generation right now, the Icon FEM generation, Elfric or Gung Ho in the UK, and C3SM, whatever the US codes are, I don't think that the FB cubed, I don't think that there will be a revolution happening with those computational patterns, if you want, in the next decades. Mainly because they are already kind of written with kind of high performance computing and parallelization and scalability in mind. They also have been developed already for decades of experience, so it's not that suddenly something will change there. The one exception is probably the spectral one, in a sense that we started with FEM mainly because of the Lejeune transformation, and we scared of the scalability. It turns out that these spectral models are still bloody efficient. So even if you run the 1 kilometer simulation, they're still actually really, really good in terms of efficiency, and more than we would thought they were like 10 years ago. So spectral models will still be there. For everything else, you're right. For everything else, we're basically talking about a stencil computation. If you have implicit time series schemes, obviously it's also like a solving issue, but yes, you're right. And I don't expect any big changes there. I don't see the new dynamical core suddenly coming up being 10 times more efficient. Given the last generation of models with Icon, FE cubed, and FEM, for example, they already were developed with all the knowledge and challenges in mind, basically.
Very cool, very cool. Thanks a lot for the insightful answers. Maybe I leave someone else. I have some other questions, but I'll leave someone else to have some questions as well.
Feel free to write an email if you want. Yeah.
Awesome, awesome.
Thank you. And Luigi?
Hello. First of all, thanks for the presentation. And my question is more about the final users and the impact on the final users. So all of these advancements, like for example, I can think that increasing the resolution can lead to more accurate results, but also open up new use cases.
Yeah.
And also, do you see different users using different methodologies, like ML-based will be more for the long range predictions, or for some types of users? Yes.
Yeah, absolutely right. So if you increase resolution, you're basically getting to this kilometer scale, and the kilometer scale is then again also the scale that the humans interact with, right? So if you look out of the window, you basically see the kilometer scale. So it's something that is really interesting in that sense, that it kind of opens new application environments. It also means that you need to kind of find better ways, for example, to represent uncertainties, because as you go to smaller and smaller scales, and you say like in 5 minutes it's going to rain, the uncertainty is probably higher than if you say like today or this morning it's going to rain, and on a larger scale, for example. So it comes with new challenges, but definitely there are new impact, like new applications as well. In particular, as you kind of reach as well, like the scale where maybe humans actually interact with the Earth system, if you want. Regarding machine learning, yeah, as I said before, I think for the 15-day time scale, it's difficult to believe that a lot of people will use like that a large fraction of the forecast will still come from conventional models in the next couple of years. I think it's really that machine learning will take over their large fraction of the market, which is fair, and it's also no problem, right? Why not? But then the forecaster at Meteor Swiss will still want to look into what the conventional model is doing. If you kind of plan a flight track from your airplane, you need a lot of like information about the vertical as well, for example, that typically can't come from machine learning models because they don't know the vertical, because we don't have enough observations, for example. So there's still a lot of some specific use cases where you want to have conventional models, and that will stay. That will be the case for a longer while. Yeah, it was a very generic answer to a generic question. I'm not quite sure whether it was satisfying, but
Yes, thank you. That makes sense.
Great, thank you. Do we have any other questions?
Langwen mentioned that you get sometimes over 80% of GPU power for machine learning models, which is, yeah, fits my expectations. Yeah.
Okay, Ben?
Sorry, I couldn't resist. Maybe because it's good that Langman brought this up, and I was wondering a bit about target hardware, because my understanding is right now GPUs are really dominating climate and weather models.
Yeah.
But do you see this being changing in the future? What like venues do you see?
So GPUs are actually not too bad for our applications as well. Right? For example, for our spectral models, so having fat nodes with a lot of memory is actually very helpful. And so far, and we're just starting to really make efficient use of this hardware as well, right? So there's a lot of room for improvements if you want on this hardware in principle. What coming after GPUs is a difficult story. It's not only a question for weather and climate. It's probably more a question of the wider domain. And I watched the GTC talk of Jensen Huang 2 days ago. I was a bit late, but it really is a bit scary if we basically realize that conventional modeling doesn't really play a role anymore for a lot of hardware developments, right? I mean, these schemes are built for FP4 rather than single position, and these schemes are built for like large language models rather than a CFD solver. So far that was not a problem, because the hardware that we use for CFD is not too different to what I mean. We can't even tell what hardware we would want to have for our models, because they're so complex to really have a co-design challenge that doesn't work, because we don't really know what we want to have, and what we so far got from hardware development worked for us well. But whether that's going to be continuing into the future, I'm not so sure with FP4 developments and stuff like this. So we'll have to see. It's not that, yeah. As far as machine learning is requiring dense linear algebra, we are going to be fine. As soon as NVIDIA stops to produce single position because they're not interested in it anymore, we're going to have a problem. But until then, we probably can surf the wave of accelerating in terms of like better bandwidth, better memory, shared memory in particular as well, and so on. And it so far worked well for us.
Oh, very cool. Thanks a lot.
I don't think we have the leverage to influence this. I don't think that really our application is big enough to change the direction of HPC at the moment with $1 trillion industry in machine learning. Yeah.
Okay, thanks a lot.
Thank you. Anyone else? Okay. Thank you a lot then, Peter, for a great presentation, and hope to see you all in 2 weeks in the next speakcast.
Thank you.
Have a great day.